So this is the third unit topics. That is first part. So first part is feedback amplifiers, and second part is oscillators. Okay. Now, so feedback means, so generally in amplifiers, we have given one input signal and we got the output signal. Okay. So that is called amplification. So amplification means you just strengthen the input signal. Okay. Suppose if the output value is not sufficient for us, okay, then we want to improve the gain, or we can improve the bandwidth for other purpose, like we can improve the input impedance also. Then we go for feedback concept. So feedback means, so whatever the output we are getting at the output side, and from the output, uh, we can connect the output sample output to input again. That is called feedback. Okay. So feedback means, so some part of output is again fed back to the input. That is called feedback. Okay. So in this, basically we have two types of feedback. One is positive feedback, another one is negative feedback. Okay. Now, difference between these two feedbacks is, see, and first of all, see this block diagram. So this is source block or input block, and this is amplifier, basic amplifier. This is output part, and this is feedback network. Okay, these are the elements in feedback amplifier. Okay, now source, it provides input signal to amplifier. So this is the mixer symbol. Okay, it compares source signal and feedback signal and generates the input signal to amplifier. That is the function of this mixer. Okay. Mm, Now, and this is beta. Beta means feedback factor or feedback ratio. Okay. The output is sampled from the load to mixer by using this feedback network. This feedback network is very, very important. Okay. Now, types of feedback. Basically, we have two types: positive feedback and negative feedback. Okay. So, positive feedback means if the input signal and output signals are both are in phase, like that means phase angle is either 0 degrees or 360 degrees. That feedback is called positive feedback. Suppose if the phase angle is 180 degrees, that means out of phase, that is called negative feedback. Okay. And in the basic, I mean, feedback concepts, these are the some important factors: open loop gain, okay, and amount of feedback. Okay, actually, we have the formula for the negative and positive feedbacks. For negative feedback, the gain expression AF is equal to A by 1 plus A beta. Similarly, for positive feedback, the gain expression is A by 1 minus A beta. Okay. So here A means open loop gain. Okay, and so there is some mistake here. So loop gain means A beta. So loop gain A into beta, but here there's some problem. And 1 plus A beta is called amount of total feedback. Total amount of feedback. Okay. Next, and for some for negative feedback, we have some characteristics. Okay, by using negative feedback, uh, there is a decrease in the voltage gain. That is a 1 point. Okay, gain value decreases, bandwidth increases. Okay, and stability also increases. We can increase the stability and we can decrease the noise. These are some features of negative feedback. Almost in all the amplifier circuits, we can prefer negative feedback. But positive feedback is used in oscillators to produce the oscillations. So later we will see the positive feedback. First of all, we will see the negative feedback. So desensitivity, some properties of negative feedback. So this is desensitivity. DAF is equal to D by 1 plus A beta whole square. And from this, DAF by AF is equal to this expression. This, okay. This is sensitivity, and desensitivity means 1 plus A beta. Next, bandwidth. So in negative feedback, the bandwidth will be very, very high when compared to positive feedback. Okay. And if we apply the negative feedback, we can improve the bandwidth. Next, interference reduction. I mean, interference means nothing but noise. Okay, so we can reduce the noise. Okay, we can decrease the distortion or noise. That is another feature. Okay, yeah, the same point here. We have reduction of nonlinear distortion. Okay, in negative feedback we can decrease the distortion. Uh, Next one, we have four feedback topologies. Okay, voltage series feedback, voltage shunt feedback, current series feedback, current shunt feedback. Okay, and see, these are the four feedback topologies: voltage series, okay, voltage shunt, current series, current shunt. See, voltage series. The first one is voltage series feedback. So voltage series means it is nothing but a voltage amplifier. Why it is called voltage amplifier means, so output here is voltage, input also voltage. Okay, therefore the gain will be output by input. Okay, output voltage, input also voltage source. That's why this is called voltage amplifier. Okay, so in voltage amplifier, we are using voltage series feedback. Next, current amplifier. So current amplifier means the output must be current, input must be also current. Okay, so this voltage current amplifier, we are using current shunt feedback. So in this figure, we are using current shunt feedback. Okay, output is current, input must be also in current. So input current means current source. Okay, that's why it is called current amplifier. Next one, this is transconductance. So transconductance means this is current series feedback. Output current to input voltage. Output current by input voltage means this is a transconductance formula. That's why this is called transconductance amplifier. And last one, trans resistance. That is output is voltage, input to current. So this is voltage shunt feedback. Last, the fourth one is voltage shunt. The output is voltage, input shunt means that there is a current source. Voltage by current is equal to resistance. That's why it is called trans resistance amplifier. So these are the differences between these four feedback topologies. So once again I am telling. So when voltage amplifier, which feedback is used? Voltage series feedback. Okay. In current amplifier, current shunt feedback. Similarly, in transconductance amplifier, current series feedback. In transconductance means current series feedback. And finally, trans resistance means voltage shunt feedback. These are the feedback topologies. Now, this is the methodology. How to calculate these feedback amplifiers. But this is not much important. And this table is very, very important. Summary of open loop and closed loop, important for some important equations. Okay. See, in four amplifiers, so these are the quantity: input, output variables, small signal model, ideal values. Okay, you please go through these values. So it is very important. Just go through this table for a few minutes. Later, I will move to next topic. Okay, and these are the some more relations. So input resistance with feedback and output resistance with feedback in four feedback topologies. Okay, now this is some example for voltage series feedback diagram. So voltage series is nothing but a voltage amplifier. Okay, in voltage series feedback, sampling is voltage and series mixing is voltage mixing. See here, so input is voltage, voltage source, output also sampling the voltage. So this is example for voltage series feedback. Both input and output are voltage signals and is said to be voltage amplifier. So this is voltage amplifier diagram. Okay, and these are the some equations, bandwidth formula, gain expression. So we are using here negative feedbacks. Okay, all the concepts are under negative feedback. So for negative feedback, this is the standard expression. AV is equal to AV by 1 plus AV beta. Similarly, bandwidth formula is bandwidth into 1 plus AV beta. See, here the gain decreases. Why I am saying decrease means AV by 1 by 1 plus. So the gain decreases by the factor of 1 plus AV beta. At the same time, bandwidth increases the factor of 1 plus AV beta. So in the starting, I said features of negative feedback. So what are the features of negative feedback? Gain decreases, bandwidth increases, stability increases, and noise and distortion decreases. Okay. So remember these features. Okay. So in this formula, so AVF means gain with feedback, or we can call gain of the feedback amplifier. AV means gain without feedback. Okay, or we can call gain of the basic amplifier. And beta means feedback gain, feedback ratio, or feedback factor. Okay, and these are the input resistance and output resistance formulas in voltage amplifier. So RIF is equal to RI into 1 plus AV beta, and R naught F is equal to R naught by 1 plus AV beta. Okay, so here input resistance increased and output resistance was decreased in voltage series feedback. Okay, next, this is voltage shunt. Okay, this is voltage shunt feedback. So voltage shunt means it is a trans resistance amplifier. Okay, here in voltage shunt, output is voltage, input is in shunt. That means it is a trans resistance amplifier, and these are the formulas. Just to remember these formulas for to solve the problems. Okay, trans resistance, input resistance, output resistance expression. Next one, current series feedback. So this is current series feedback and nothing but trans conductance amplifier. Current series means this is the equivalent circuit and these are the equations. Okay, see these formulas. Then this is a simulation output. Mm. So gain and phase margin. Okay. This is the gain margin and this is called phase margin. And these are the effects of phase margin and closed loop response. So we have some equations here. See, in the gain margin on x-axis I am taking the frequency by omega. Omega means frequency, and y-axis is dB. I mean gain. So initially there is a gain, some maximum gain. After when the frequency increases, the gain value slowly decreases. Okay. In the similar way, this is a phase margin. That means phase angle versus frequency. Okay, this is the response between phase angle and frequency. See this graph, and these are the some important points about phase margin. Okay, so this is about feedback concept and feedback amplifiers. Okay, so what we have seen up to now. So feedback definition. Okay, so feedback definition and types of feedback. So feedback means output is some part of sampled output is again connecting to input. Okay, that is called feedback. Then what is the use of this feedback? We can change the bandwidth, we can change the resistance, we can change the gain. Okay, so based upon the applications, we can use any feedback. Okay. Mm. So basically, we have two feedbacks: positive feedback and negative feedback. So positive feedback means input signal and output signal both are in phase. That means phase angle should be 0 degrees or 360 degrees. And here one thing I forgot to tell. So this positive feedback is also called regenerative feedback. So another name of positive feedback is regenerative feedback. Why mean? By using this positive feedback, there is an increment in the voltage gain. That's why this is called regenerative feedback. Similarly, negative feedback is also called degenerative feedback. What is the reason? The gain value decreases. That's why negative feedback is also called degenerative feedback. Now, features of positive feedback and negative feedback. So, first we see the features of negative feedback. So, in this first part, all the topics about negative feedback only. So, negative feedback. Today we are preferring negative feedback means the negative feedback, bandwidth increases, stability increases, noise and non distortion decreases. So these are the advantages of negative feedback. Okay. So in negative feedback, again we have four feedback topologies. So what are the four topologies? Voltage series feedback, voltage shunt, current series, current shunt. Okay. Now voltage series means so output is voltage, input must be in series connection. So it is a voltage amplifier. A voltage amplifier. Why it is called voltage amplifier? Output voltage, input also voltage. Voltage by voltage. It gives voltage gain. That's why it is a voltage amplifier. Next, voltage shunt. So voltage shunt means it is a trans resistance amplifier. So why it is called trans resistance? Output is voltage, input is current. That's why it is trans resistance amplifier. Similarly, current series feedback. So in current series, output is current, input is voltage source. Current by voltage is called transconductance. So that's why it is the transconductance amplifier. And last one, voltage shunt. Sorry, current shunt. So current shunt, output current, input also current. Current by current, it gives current gain, so that it is called current amplifier. This is about the feedback. Next, in each feedback, we have seen the formulas. I have shown this comparison table. So, so these are the important equations in four feedbacks. Okay, RIF. RIF means input resistance, RNIF means output resistance with feedback. Similarly, gain relations. Okay. After that, we have seen example circuits for four feedbacks. Okay, so this is for voltage series feedback diagram and voltage series. These are the formulas: bandwidth, RIF, RNIF, AVF, etc. Similarly, okay, just a minute. And this is voltage shunt. Okay, then current series feedback and current shunt feedbacks. And these are the formulas and the responses. Gain and phase margin. Okay, so this is about the first part, and next part is about oscillators. Okay, so in oscillators we are using positive feedback. I already told in the earlier of the class. So positive feedback. So with this positive feedback, we can generate the oscillations. Okay. So positive feedback means input and output signal both are in phase. That means both I mean in phase means phase angle is 0 degrees or 360 degrees. Okay. Now, mm, so what are the features of positive feedback? Okay, with this positive feedback, we can improve the gain, but bandwidth decreases, stability decreases, noise and nonlinear distortion also increases. So whatever the features we have discussed so far for the negative feedback, in the opposite way, opposite manner, these are the features for positive feedback. Okay, in positive feedback, only one advantage, that is gain value increases, and remaining are the drawbacks. So that's why in almost all amplifier circuits, we are preferring negative feedback than positive feedback. Okay. See, this is the difference between amplifier and oscillator in this figure. So in amplifier, we have input signal, but in oscillator there is no input signal. So oscillator means it produces output signal without any input signal. That is the definition of oscillator. Okay, for oscillator there is no need of input signal, even though we will get the output signal with the help of positive feedback, especially. Okay. So in oscillator, we have only one input, that is DC input, and we will get the AC output. So this oscillator converts DC signal into AC output signal. Okay. See, see. The electron circuit used to generate output signal with constant amplitude, constant desired frequency is called oscillator. It is also called waveform generator. So another name of oscillator is waveform generator. Okay. The primary function of oscillator is convert DC power into periodic AC signal. So just now I told now. Okay, oscillator does not require any external input signal to produce the sinusoidal output signal. So this is about oscillators. Okay, and this is block diagram of feedback amplifier, oscillator feedback network to amplifier. Okay, now coming to oscillator theory. So mostly here we can use the Barkhasan criteria. See, so in this figure, the first one is from the source signal. This is the mixer block. This is mixer. This is the output block, and this is feedback network. Okay. According to Barkhasan criteria for positive feedback, the total feedback, total phase shift must be 360 degrees. Okay. Now, 360 degrees or 0 degrees. Okay. Here we are giving the input signal. The input signal will be amplified with this amplifier, and we will get the output signal. And the output signal is fed back to the input by using this feedback network. And both input and feedback signals are same thing. It looks like similar. That's why the phase angle is 0 degrees or 360 degrees. So that it is called positive feedback. Okay. And this for positive feedback, the gain expression, and this is the derivation of AF. AF is equal to A by 1 minus A beta. That is a gain expression in positive feedback. See this derivation. Already we have done the derivation in our regular classes. Just go through this derivative part. Okay. So this is the derivative part. See the Barkhausen criteria. So according to Barkhausen criteria, the total loop gain must be unity or greater, and another statement is the total phase angle is 360 degrees. Okay. See, here we have taken an inverting amplifier. So what is inverting amplifier? It is an amplifier which produces 180 degrees phase shift. The best example for inverting amplifier is CE amplifier, common emitter amplifier. Common emitter amplifier gives 180 degrees phase shift between input and output. Okay. So in this figure, we have taken CE amplifier for suppose that is inverting amplifier. So from the inverting amplifier, you will get the 180 degrees phase angle. See, this is the input signal and this is the output signal. Both are out of phase. And this sampled output again we are connecting to mixer using feedback network. See, this signal both are same. And after using feedback network, and again there is a change in the direction, polarity. So the phase angle between these two is 180 degrees. And okay, and the same signal we are giving to input. So finally, input signal and output signal and this feedback signal both are similar. So what is the phase angle now? So from inverting amplifier you are getting 180. From feedback network you are getting 180. So 180 plus 180 total phase angle is 360 degrees. So that it satisfies the Barkhausen criteria. That's why it is called positive feedback. See this theory. So whatever I have explained now, the same points will be here only. So you please go through these points. If you have any doubts, please ask. Okay. Now, types of oscillations. So nature, we have different types of oscillations. One is sustained oscillations, growing type oscillations, decaying type oscillations. Okay. So first, sustained oscillations means the amplitude and frequency must be same. Okay. Amplitude also constant, and time period must be also constant. That is called sustained oscillation. For sustained oscillation, this is the condition. Mod A beta is equal to 1. Next, growing type oscillations. For this, the condition is A beta is greater than 1. This is called growing type oscillation. Next, decaying type oscillations means like this. Okay. So for decaying type, the amplitude is decreasing slowly, exponentially. This is called decaying type oscillations. The condition is mod A beta is less than 1. Classification of oscillators. Okay. We have various categories based on according to circuit components, according to frequency, okay, according to feedback. We have various types of oscillators. So, according to waveform, we have sinusoidal or non-sinusoidal oscillators. Okay, if you get the output in sinusoidal, it is called sinusoidal, and if the output is like non-sinusoidal, they are also non-sinusoidal oscillators. According to circuit components. I mean, based on inductance, capacity, inductive LC oscillators, RC oscillators. Similarly, according to frequency, audio frequency, radio frequency, high frequency oscillators. These are all the frequency based on frequency oscillators. Next, based on feedback. Okay, these are the feedback oscillators. Feedback oscillators, non-feedback oscillators. One is feedback oscillator, another one is non-feedback oscillators. Okay, and for non-feedback oscillator, example UJT relaxation oscillator. It is a example for non-feedback oscillator in which there is negative resistance region. So UJT means unijunction transistor. It exhibits negative resistance character. Okay, and some of the signs are under the above category. Like means for non-sinusoidal oscillator, then these are the examples. Tuned circuit, LC circuit, RC phase shift, crystal, heterogeneous. There are some examples for the oscillators. Let's see. The first one is RC phase shift oscillator. Okay, this is the RC oscillator, and here this is one RC network, and these are the three RC networks connected in a ladder shape. From each RC network, we will get the phase shift around 60 degrees. Okay, now the total phase angle is 180 degrees from RC network. And what about the remaining 180? The remaining 180 is obtained from amplifier. Okay, okay, so this is the block diagram of circuit diagram of RC phase shift oscillator. So here this is an inverting amplifier, and this right side part is feedback network. Okay, so from this amplifier you will get 180 degrees. From this inverted feedback network you will get 180. So 180 plus 180 total 360 degrees we are getting. So it satisfies the Barkhasan criteria. Okay, and this is the frequency formula in RC phase shift oscillator. 1 by 2 pi RC root of 6 plus 4 RC by R. We can say RC by R is equal to K. And that K value is very, very small. We can neglect K also. So finally, this is the formula. 1 by 2 pi RC root 6. And this is the gain expression. This is a condition for sustained oscillations. HFE mean is equal to 4K plus 23 plus 29 by K. Here K value, K means RC by R. Okay, already you have learned the derivative part in regular classes. Here, no need to derive this. Just remember the frequency formula and the gain expression. These two are enough. Okay. Now, these are the advantages. Advantages of phase shift oscillators. Advantages and disadvantages. So please read this point for 2 minutes. Okay, these are advantages and disadvantages. Next, we will see the Wayne bridge oscillator. So, in Wayne bridge oscillator, okay, yeah, here I have 0 degrees phase shift. There is no need of here inverting amplifier. Okay, no need of to using inverting amplifier. This is the simple network, RC network. This is one RC network. This is another RC network. These two are connected in series. These two are connected in parallel. Both are in series. So this is the major section in the Wayne bridge oscillator. Okay, and these are some calculations. See, this is the circuit diagram of transistorized Wayne bridge oscillator. Okay, this part is multi two-stage amplifier. Okay, from this two-stage amplifier, you are getting 0 degrees phase shift. From feedback network, you are getting 0 degrees phase shift. Total phase shift is 0 degrees. Okay, and this is the theory part. And the frequency expression is 1 by 2 pi RC root 6 from Wayne bridge oscillator. This is the frequency expression. Second. Yeah. This is a 1 by 2 pi RC. This is the frequency expression 1 by 2 pi RC. Okay. So actual formula is 1 by 2 pi root of R1 R2 C1 C2 from this figure. Suppose if the R1 is equal to R2 is equal to R and C1 equal to C2 equal to C, then the formula will be 1 by 2 pi RC. So similarly, and see the advantages and disadvantages. See advantages, disadvantages of Wayne bridge. Okay. Next, this is about RC oscillators. So till now we have seen RC oscillators. One is phase shift oscillator, another one is Wayne bridge oscillator. Now next we will discuss about LC oscillators. So LC oscillators, here the main elements are inductor and capacitor. Okay, that too in feedback network. In our LC oscillator, we have two types of oscillators. One is Hartley oscillator, another one is Colpitts oscillator. Okay, so here the major difference between Colpitts and Hartley is in feedback network. Okay, in feedback network, if we have two capacitors and one inductor, that is called Colpitts. Suppose two inductors and one capacitor, that is called Hartley oscillators. See, this is the Colpitts oscillator figure. So this is amplifier section, and this is feedback part. So here we are using two capacitors, one inductor. But in case of Hartley, we have two inductors and one capacitor. Okay, and the frequency formula is 1 by 2 pi root LCT, where CT is equal to C1 C2 by C1 plus C2, total equivalent capacitance. So FR means resonant frequency. Okay, this is Colpitts oscillator. Similarly, and in and this is the some example problem. Next. And these are the applications of Colpitts. Okay, now let's see the Hartley oscillator. Okay, this is Hartley oscillator. See, just it is similar to Colpitts. The only difference is in the feedback network. Okay, here two inductors and one capacitor. Okay, and this is the formula. Resonant frequency F is equal to 1 by 2 by root LTC, where LT is equal to L1 plus L2 plus 2M, where M is equal to mutual inductance. Okay, mutual inductance between the coils. Okay, Hartley oscillator example, some example problem. summary and basic LC oscillator, some damped oscillations, and resonant frequency Fr is equal to 1 by this is standard expression for resonant frequency. Fr is equal to 1 by 2 pi root LC. Okay. And these are the example problems. And this is LC oscillator summary. Let's read these points. Okay, okay, guys. This is about some important oscillators, and apart from these, we have some other oscillators like crystal oscillators. Okay, Colpitts crystal oscillators. So in there, we can use some piezoelectric crystals. Okay, so till now we have seen some basic oscillator concepts. Okay, types of oscillators and types of oscillations. Then we have seen RC phase shift oscillator and the Wayne Bridge oscillator and equations, frequency formula and gain expressions. Similarly, in LC oscillator, we have seen two types. One is Colpitts oscillator and Hartley oscillator. Okay, mm, where we can see the frequency formula. In Colpitts, we have a formula M is equal to 1 by 2 by root LC equivalent. C equivalent is equal to C1 C2 by C1 plus C2. Similarly, in Hartley oscillator, the gain expression is 1 by 2 by L equivalent C, where L equivalent is equal to L1 plus L2. Okay, so this is the second part in third unit. So as first part we have seen feedback, and second part we have seen oscillators. Okay, okay, students. Thank you and all the best.